All right, so what we have is a conveyor, but they tell us the angle is 15 degrees below the horizontal. So it's like this, and this angle is 15 degrees. Okay, but we can make it just like an inclined plane. This angle here would still be 15 degrees. Okay, so I'm just going to draw it like we would a normal inclined plane so it doesn't look confusing. Okay, so we've got this conveyor. We know that it's angled 15 degrees. We know that this is 2.5 meters higher than the bottom of the conveyor. Okay. We know that there's a frictional force of 150 newtons. So is that going to result in the object having more or less energy at the bottom? Less. It's going to take it away. It's not like yesterday where we were pushing the car down the ramp and actually adding energy to the system. In this case, friction's taking it away. All right. The other thing we know is that at the top, okay, the objects are moving at 0.75 meters per second. So they do have some kinetic energy at the top. Okay? They'll obviously have kinetic energy at the bottom as well, right? So we need to set this up just like we would any other work energy theorem question. Work is the change in mechanical energy. So that means that force times distance, and I don't need the cos of theta part here. Whoop. I don't need the cos of theta part because the force parallel is in the same direction as the movement. Okay, is going to equal our final mechanical energy minus our initial mechanical energy. All right, so what I'm looking for is going to be part of this, right? So I can move the mechanical energy right now, or I can wait till I add in all the other formulas. It doesn't really matter, right? So I'm going to say force times distance equals m times g times hf plus 1/2 mvf squared minus 1/2 mvi squared plus m times g times hi. Are any of those 0? Stephen, any of those 0? Yeah, final height is 0, so that means that my final potential energy is also 0. All right, so I can take that right off, don't have to worry about it anymore. Now, I'm looking for this, so I need to move essentially my initial mechanical energy over to this side. And it's very much like what we had yesterday, where we have the force times distance plus, or the work, plus the initial mechanical energy. So 1/2 mvi squared plus mghi is going to equal 1/2 mvf squared. All right, since I'm looking for vf, I'm going to divide both sides by 1/2 of m. It's going to come over here, and then I'm going to square root to get vf. So it's exactly the same as yesterday in terms of the manipulation. What's going to be different from yesterday is that the object is going to be going slower at the bottom rather than faster. Okay, so we have here, okay, that we're going to have force times distance, but that force is going to be negative because it's friction. Okay, that's where we're going to get the loss of energy from. So we'll have negative 150 times the distance. Now, did they ever tell me how long this ramp is? Can I calculate how long the ramp is? I have one side and I have the angle. All right, so to calculate the hypotenuse of this ramp, okay, I'm going to use sine. So I'm going to go 2.5 divided by the sine of 15. Okay, that'll give me my hypotenuse. So the hypotenuse is 9.659 meters. Okay, and then I'm adding on to that my 1/2 times the mass of the crate, which was 200 kilograms. And it was moving at 0.75 meters per second at the top. And I've got to add on my potential energy. So 200 times 9.81 times the height, which was 2.5 meters. And then I'm going to divide all of that by 1/2 times 200. All right, so there's the amount of friction that's going to be involved. So, whoop, negative answer. Okay, and I'm going to add on to that the kinetic energy, so 0.5 times 200 times 0.75 squared. Okay, and then I'm going to add on to that the potential energy. Okay, there we have it, and then we're going to divide that by 100, because that's half of 200, and then we'll take the square root of that. All right, so we're getting 5.92, 5.93, okay, meters per second at the bottom of the ramp. Okay, everybody with me on that one? Okay, questions there? All right, before we do this question, we're gonna put. All right, so we've got the rock that's gonna fall down. Now, if it's being dropped, initially it only has what kind of energy? It only has potential energy. So we're still going to say that work is a change in mechanical energy, but we're going to recognize that we only have potential energy at the beginning. So we'll say m times g times hi. Okay, and at the end, we're at the bottom. Okay, that doesn't have any potential energy at the end, but it's moving at 4.5 meters per second. Okay, so really, that's all we have in this question. That's the change in mechanical energy. Okay. Now, it is working against friction, so this frictional force here of 800 newtons is going to have to be negative, okay, in order for this to work out right. Okay? But I'm looking for the initial height the rock was dropped from. Right? So I'm going to bring the 1/2 mvf squared over, but I'm going to add or subtract it. I'm going to have to, well, actually, we can do it this way. Let's make it simpler. I'm going to bring mghi over here. So I'm going to have fd plus m times g times h initial equals 1/2 mvf squared. Okay, I want this, so I'm going to bring fd over to this side by subtracting it. Okay, that way I've kind of made it negative thing. All right, then I'm going to bring the mg over here. Okay, and now I'm solving for hi. Right, don't have to square root anything or anything like that. All right, so hi is going to equal, okay, 1/2 times, what did we say this thing was? 400 kilograms. Okay, 400 kilograms times, was 4.5 meters per second, is that right? Yeah, 4.5. Whoop, I'm not going to put that on there. Okay, and that's going to be squared, okay, minus negative 800 times the distance that it rolls for, and it rolls for 30 meters, divided by 400 times 9.81. Okay, that'll give me the initial height that this thing was dropped from. Okay, so we got 0.5 times 400 times 4.5 squared. Okay, so there's our kinetic energy. Okay, and we're going to add on to that 800 times 30, because subtract the negative. Whoop. Keep doing that. Okay, 800 times 30. Okay, and then we're going to divide that by 400 times 9.81. All right, so it was dropped from 7.15 meters. I think we only have two significant figures, so it's 7.1 meters. Okay, so these all worked pretty much the same. Okay, all we've said is that work is a change in mechanical energy, and then we've put in the formulas for potential and kinetic and moved things around until we solve for what we're looking for. Okay, there's nothing like algebraically or mathematically difficult here. The issue is, can I figure out what things are going on, what kind of energy changes are happening. All right, now I'm going to have you work on some that are we'll start like entry level and we'll kind of work our way to more complex, because these are the ones we walked through. Okay, so in the workbook for Unit 2, okay, we'll call these up and I want you working on them for a while. Okay, so for number 5 here, we've got a 90 Newton box. So they give us the weight of the box, not the mass. Okay, is pulled 10 meters along a level surface by a rope. Okay, the rope makes an angle of 20 degrees with the surface, and the force exerted through the rope is 75 newtons. Okay. So we know this angle here is 20 degrees, and we know that the force is 75 newtons here in the rope. Okay, we're looking for how much work is done on the box. Well, it mentions nothing about friction or anything like that. Okay, so this should really just be work is F cos of theta times d type of question, right? So we would have our force of 75 newtons, okay, times the cos of 20, and it's pulled 10 meters, right? So times 10, right? Should come out to 705. Yep, 705, yeah, joules, right? Okay, and guys, that's something else. In looking at the everybody jump activity there from the other day, I had a lot of people who were putting newtons down as the units for work and energy. Okay, what are the units for work and energy? Joules. Okay, makes a big difference, and you're going to lose a mark on the answer if you put in the wrong units, right? So make sure you're putting joules for work and energy. Hey, any other ones giving us trouble? Everyone's still good?